Okay, so now let's look at the problem number 21. A firefighter, a distance d from a burning building, directs a stream of water from a fire hose at angle theta initial above the horizontal as shown in the figure. If the initial speed of the stream was v initial, at what height h does the water strike the buildings? Okay, now let's draw a picture which helps us to understand better and can help us easily solve the problem. Okay, so here we have a fire hose which has initial velocity, which has angle initial. Okay, let's just keep it theta. Then strike the water, then it hits at certain height. Okay, this height is h and this is a distance, so we have to find what is the h if d is given. Now, before solving such a problem, we have to resolve x and v into x and y components. We have to write down equations for the d and also for the h. Now, for the simplicity, let's say that our d is equal to x, okay, and h is equal to y. Now, we know that in this case we have a coordinate system. So this is our initial, so x initial, y initial, right? In both cases it's 0 and 0. Now at this point we have x final position, and at this point we have y final position. Okay, so this is in x, that's one is y. Let's resolve v initial into two components. This component will be equal to vx initial, which is equal to v initial cos theta, and the y component, let's call it vy initial, is equal to v initial sine theta. Okay, what else? We also know that the velocity in the x component is a constant, so that means we can say that vx initial is also equal to vx final. We also know that a g is pointing downward, which is minus 9.8 meter per second squared. We also know that in the acceleration x direction is equal to 0. Now, if we know all these things, then we have to understand one thing. When the water is coming with initial velocity, then the time to reach x final is certain time, right? So that means, let's write down the equation. We know that x final is equal to vx final multiplied to the time. Okay, this is when the water hits this, reach that position, x final. Now that means we can say that here t is equal, how much time is needed to hit that x final. So the time is then equal to x final divided by vx final. Okay, now then we can write down another expression, another formula for y final. So we have a general formula, which is delta y is equal v y initial t minus gt squared over 2, right? Now, delta y is simply y final minus y initial. We know that initially y initial was 0, so we just keep y final, which is equal vy initial. Vy initial is equal to v initial sine theta. That means we can say that it's v initial sine theta times t minus gt squared over 2. Now, we also know that here x final divided vx final, which is equal to vx initial, and vx initial is equal to v initial cos theta. V initial cos theta, correct? Now, we got the time that it reached x final position, which will be the same for the, if you substitute into t, we can get at what height or what will be the y final position. So we have to plug the t inside the t and we will get what we want. So that means we can say that y final, which is equal to v initial sine theta, t is equal x final divided v initial cos theta minus g over 2 x final v initial cos theta squared, right? So then we can have y final, which is equal to this v initial will cancel, x final tangent theta minus g over 2 x final squared divided by v initial squared cos squared theta. Okay, then finally we can say that our y final, or in other words the h, is equal to x final, which is a distance, multiplied to the tangent theta minus g over 2 d squared over v initial squared and cos squared theta. Okay, that's how we solve this problem.